We need to define this a little bit so that we can then look at some of the theory to help us understand how it is that these samples that seem to vary so much from sample to sample can actually be used to accurately predict something from the population. So we're going to start with this idea of a sampling distribution. If we were to create a distribution formed by values of a sample statistic for every single possible different sample in that population of the same size, that's our sampling distribution. Now, of course, we would not find every single sample that's possible out of a population because that completely defeats the whole idea of using a sample to make predictions about the population. But we're looking here at the theory. So theoretically, if we were to consider every single possible sample, then it would have a lot of different values. And we want to look at those different values so that we can see some important information about the variability of the values in this of a particular statistic. I've been talking about this p-hat frequently, and just in case we have forgotten what p-hat represents, just remember that p-hat is your sample proportion of successes. So it's simply calculated by taking the number of successes in the sample and dividing by n the sample size. So let's take a look at example 8.2. So this was a study done in fall 2015 when there were 20,944 students enrolled at California Polytechnic State University, and I don't know how to pronounce that, San Luis Obispo, maybe. But of these students, 9,082, which is 43.4%, were enrolled in a STEM major. Now, what would you expect to see for the sample proportion of STEM majors if we were to take a random sample of size 10 from the population? So we could do a simulation here, like we did before, where we continued to take samples of size 10 and calculated the proportion that were STEM students. So this histogram represents 500 random samples of size 10 from this particular population. Now, I want you to look at this histogram, and it should look familiar from chapter 6. It should remind you of a normal distribution. Now, it's not quite normal, but it is starting to have the properties of a normal distribution. And that is not a coincidence. That is actually going to happen in these sampling distributions. So we still see that sample-to-sample variation in these different p-hats. If you look closely at these numbers, there's an awful lot of variation. Some of these samples had no STEM majors, and others had 90% STEM majors. Even though most of them were there in the middle, which we would expect since the true proportion was 43.4%, but there was so much variation here that it would have been relatively likely that we ended up with a really big or really small estimate. So size 10 must not be a good enough value in order to estimate from a sample for the proportion. Now, we also concluded that 20 might not be good either. But I want us to look at some additional sample sizes. So these simulations are coming from sample sizes of 50 and sample size 100. So the top left is that sample size of 10, and then the top right, there was also a 25, then a sample size of 50, and then sample size of 100. Now, since these were all on the same scale so that you can make comparisons, you might not completely see the approach to a normal distribution. But that first histogram really is a little more triangular. It is starting to look normal, but it's not quite that distribution where 68% is there within one standard deviation. Now, it looks like when you go to B that there's more variation, but I want you to see that the overall variation went down. We're now only looking from 0.2 to 0.7, and we do seem to be mounting a little bit more there in the middle. But it's not until we see our samples of 50 and 100 that we really get a better normal distribution where there's a big bulk there in the middle. And we also see that as the sample size increases, the variability from sample to sample decreases. We rarely saw those extreme proportions when we had a sample size of 100. It just wasn't common for us to get a sample here that had a value that was really different from the true proportion. Whereas when we had a sample size of 10, it happened kind of frequently that you got something as low as 0.1 or 0.2, or something as high as 0.7, 0.8, or even 0.9. That simply did not happen in our sample sizes of 100. So I want you to think for a second, why might there not be as much variability? Well, think about taking a larger sample. That larger sample is going to better reflect the population because you're looking at more people. See, it would be relatively easy to find 10 people in your sample and none of them be a STEM major. But it would be a whole lot harder to take 100 people and not find any STEM majors. So hopefully you can think about the probability there that when you take a larger sample, there's just not as much of a chance to have something that's so much different from the true population. So as you look at these histograms, you should notice that they are relatively symmetric, and that is certainly something that you would expect. Now, if we had actually done these samples with every single possible sample instead of just 500, each of these histograms, believe it or not, would have actually been centered at exactly 0.434. And that is a super powerful observation. That even though there was different amounts of variation, all of them would be centered at the true proportion. Now, as the sample sizes got larger, then the histograms were not spread out as much. So what does that tell us about these sampling distributions? Well, there's a few properties that we can state about these sampling distributions that's going to help us as we learn the different statistical inference methods. So the first one is that the mean of the sampling distribution, that p-hat distribution of all the samples, is going to be exactly equal to the population proportion. The standard deviation of that sampling distribution is going to equal the square root of p times 1 minus p over n. Now, if your population is infinite, then that will be the exact standard deviation. However, most populations are finite. It's pretty hard to have an infinite population. So that standard deviation is going to be approximately correct as long as your sample isn't more than 10% of the population. That might seem a little counterintuitive because I told you had to have a big enough sample, and now I'm telling you have to have a small enough sample. Well, you have to have both. You have to have a big enough sample to see that variability go down, but you also have to make sure that your sample is small enough so that it's no more than 10%. Otherwise, these rules don't work. And then one thing also to notice when your n is large, and as long as p is not too close to 0 or 1, as long as it's somewhere kind of in the middle, then the sampling distribution will be approximately normal. And so we can use all of the stuff that we learned in Chapter 6 about normal distributions to answer questions. Now, the further you get from 0.5, then you'll have to have a larger n in order to make this normal approximation. So a conservative rule that you can apply to ensure that you're going to get a relatively normal distribution with these sampling distributions is you take your sample size times the true proportion, and that should be greater than or equal to 10, and then your sample size times 1 minus the true proportion should also be greater than or equal to 10. Another way of saying that is that in any given sample that you should expect to have at least 10 successes and at least 10 failures in that sample.